Okay, so this is what we put together in the last video. It's the OLED display. I'm having a lot of issues with one of the cameras, the front-facing camera. Let's see if it works. Hey, there it is. Cool. Hello. So this circuit here is an I2C circuit. In the last video, we were talking about the ADC multi-channel, but at the end of the video, we put this circuit together. So if you are new here, you might want to see the previous video before it goes into the members area on putting the circuit together. But it's just going to, you can probably see what's going on here. The circuit is essentially viewable. So the I2C, what is that? The I2C pins that we're using is, I think it's 59 and 58. So those two, see if I can get a little bit closer. Yes, 59 and 58. And I'm going to try to get a view of the pins. So the SCK is on 58 and the SDA is on 59. And I have a 100 microfarad capacitor and a 0.1 microfarad capacitor to stabilize the power. I was having some problems getting this to work last Saturday. It would work intermittently when I powered it on. In fact, I actually thought it was a bad display until I used these capacitors to mitigate any problems, because of the use of breadboards is really bad in prototyping, unfortunately, because of all the metal, all the tie strips act as antenna, and it's not a good it's not a perfect way to do prototyping, but it is a quicker way to do prototyping. I may not actually need these when I put the circuit on an actual PCB, so I probably will try that later on, because I want to put the accelerometer and this display on a circuit, and I'll probably work out a PCB during a live stream and see how that looks and how it works. But I might still add a couple holes or vias or pads for a capacitor, both of these, and I'll try it with and without in that actual circuit and see if it works. I'm going to get a lot of notifications, I think, because of the hurricane today, so I apologize for that. Go to my channel here because I want to see a better view of the comments. Okay, good. Hi, MyTech. How's it going? Welcome. Okay, so hopefully you can see me, and I might turn off my front-facing camera. I mean, I'm going to be working with the circuit, and also I'm going to be putting the program on the screen as well, so I'll turn that off for the time being. So in the circuit, I'm not using, in an I2C circuit, you generally want to pull the SCK and the SDA high with resistors, a 4.7K resistor on both the SDK or SDA and SCK lines. I didn't do that and it worked, so I'm going to take a look at the program. I'm wanting to sort of decipher the program that was created by Claude. I used Claude because the datasheet for this, I could not find it. I could find the datasheet for the actual display, but it's using these pins down here for its datasheet, and I'll show you that datasheet. So the information on this, if Claude has the information, why not use it? And what I'm going to do, because I have a full set of I2C videos on my channel. In fact, I have most of them. The other two, there are three that are missing from the series because it was for exclusive content for Patreon members. But I'll probably make those available soon. After I make this video, because I'm just going to be repeating the information anyway. And that one was for an accelerometer, a low G accelerometer. So I'm going to show that, what do you call it, the datasheet. I'm showing this datasheet to you because I feel that it's important to understand what you can find out there, or lack of what you can find out there, what you can't find out there, in terms of this stuff. So this is, I'll try to find it here. All right, I'm going to switch to the display. All right, so this is the datasheet that I found for this display. And you can see that it looks like the data pins that you would normally see in an LCD, like the 20 by 4 LCD that I've shown how to interface in quite a number of videos on my channel. So it's showing that, but I2C, the commands or the addresses and the registers are different, completely different. So it's not showing this to you for the I2C communication, but it does show SDA pin here, which is kind of interesting. So I'm not sure why it shows that, but it doesn't show all of the addresses for communication with that display. So I think the best way to go over this I2C is to sort of look at the program that I was given by Claude, which I've already put in the IDE, and decipher it, talk about it, explain what it's doing, I guess. And by the way, prior to this live stream, I watched all of my I2C videos. This was made 6 years ago, and man, it helped me. It really did sort of like make me understand I2C again. So, and I'm not sure. There's not too many videos out there that I've found that really talk about the I2C and a bare chip, just interfacing I2C straight to a bare chip, you know, not using Arduino or a development board like the Nucleo. So first I want to decipher the I2C stuff and the preparing these pins of the microcontroller for use with I2C. So let's take a look at that. One moment while I bring up the program. And if you guys have any questions, just go ahead and put them in the chat. I can answer any questions along the way. I have it going on in Twitch. It says it's unstable. I'm not sure what that is all about, but I see it says offline. Wait, I haven't started it yet. Okay, now Twitch has been started, so let's see if that works. SOS, thanks for coming in. I usually never catch the live stream because I watch 1.5 times or so, but maybe I'll stream on my computer live in the background and watch later at speed on my phone. Yeah, that's a good idea. Just a word of on sort of housekeeping stuff. The videos, the live streams will be available in the live area for 1 week. After that 1 week, it'll go to the members area. But before that, on the same day, what I've done in the last 2 videos, I've created a supercut for each of these videos. But the supercut is going straight to the members only area. So it's something that I can provide them as a benefit for being a member. So if you want to get a supercut, consider becoming a member of the channel. All right, so let me open up the STM cube. I know you can't see this yet. I will turn it on in a second. CNC, thank you for showing us how to do with just the chip. Yeah, not a problem at all. Okay, I wrote something on the display I want to take out first because I don't want you guys to see that. It's private. I wrote a little message for my son on it. So let me get rid of that. All right, so I'm going to go ahead and switch to the display. All right, is that large enough or should I make it larger? Let me do this here. I can probably put both on the video at the same time. One of these days I'll have presets made. CNC is actually helping me with this stuff. CNC time-lapse, he's helping me with a lot of this stuff. So I really appreciate that. He is a master at video and can't wait to actually implement what he suggests for me. Yeah, let's see. All right, so I'll make the video larger, or the you probably hear me kissing my teeth a lot. That's a Jamaican thing. All right, so I'm going to bring this down and use the Control Shift plus, because Control plus doesn't work in the Eclipse IDE. How is that? Does that work? All right, awesome. And also go check out CNC time-lapse video, or his videos on his channel. He's trying to start that up, and they're good quality. It's good quality videos out there on his channel, and all around nice guy, good guy, because he's also helping me with my business. So yeah, give him some love over there. Okay, so let's see. All right, you don't need to see that little bottom part. All right, so this is the main. I just lost my area here, lost my way. All right, here we go. All right, so the main is where the program enters execution. This is the first thing it goes into, is the main. And once it goes in here, it does all of these these functions, and it's pretty clean. I mean, the main, it sets up the clock, sets up the I2C, initialization, creates a delay, because we may not actually need this, because I was playing with delays to get the thing to work a little bit better. But I think with the capacitors, we won't need this delay, but we can test it. Then we initialize the OLED, we clear the OLED, and then we do stuff with the OLED, the display. So I'm playing with drawing rectangles and circles and things like that. About 90%, 99% I would say is well, 90% of this is created by Claude. And I also did try Claude and Chat GPT. I tried the new 01 preview, and I couldn't get anything to work with that either. So Claude really is the only LLM that I can get this to work for microcontroller projects. I mean, single shot, I guess I would call it, or maybe not single shot in this case. This took probably a few trials, but it was mainly because of the not using the capacitors. That was one of the reasons why I couldn't get it to work, and it took me pretty much all day Saturday to get this to work. Okay, is this dev better in Eclipse or Visual Studio or VS Code? This is from CNC, or is it just preference? Limitations in one or the other? I would say this is really not. This is Eclipse. The background is Eclipse, but it's considered the STM32 Cube IDE. They've this is their sort of IDE, but it's based on Eclipse. So Eclipse is sort of the foundation. With Visual Studio and VS Code, you can get it to work, but you have to set it up, and the setup is very difficult. And because I'm working with single chip, and most people think it's more difficult than doing it with like sort of an Arduino and using the Sketch environment, I want to make sure that this is easy as possible, so they can understand it and get going pretty quickly. So essentially all you're doing is you're installing the STM32 Cube IDE and writing the program, making sure that you have the correct programmer, and setting that up in the run configuration, which I talk about in my book quite extensively, and also in my previous videos. And that's it. You just program it, and as long as you have a circuit that works, you're good. And like, just to sort of drive that home, in an Arduino, you'd have to plug this in, and you'd probably still have to use all of this circuitry anyway. So you know, why go there when you can just do it from a lower level and still be as, you know, understand it just as easily. Okay. But VS Code and Visual Studio, there's a lot of setup. There's also, you could do it in Vim. You can use probably Programmer's Notebook that I talk about in other videos. I used to use Co-IDE, which is by Kukox, and that went, I think they stopped supporting it, and it went by. The programming is identical. So you could watch all of those videos and still use all the videos almost verbatim, and it'll work in STM32 Cube IDE. Okay, so let's take a look at the system clock config is kind of important because what Claude did is put it into 48 megahertz. So it, and also just to note, 48 megahertz, you will not be able to set up 48 megahertz unless you have these two pins powered. This is generally for the ADC, but it also enables clocks, certain clocks, higher speed clocks. So it's good to have these two powered, these two pins. Okay, Skeptic, how you doing? Thank you for coming in. Okay, the mic is clipping. Let me do some tests then. Testing, is this better? Let me know if the mic is clipping. Testing, my name is Patrick. Testing, you should get some clipping pops, potentially. Okay, so while we're testing that, all right, good. Thank you, Skeptic. CNC says, I've only used Eclipse for some Java projects back in the day, but I've started out in Borland C++. Oh my God, that brings back memories. I used Borland C++ as well. That was a long time ago, before discovering Visual Studio back in the early 2000s. Too low, might need to come up a little bit. Not clipping. Okay, let me just see if I can. Okay, is this better? Testing, 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 testing. My tech says sound is not good. Testing, testing, 1, 2, 3. Hello? Okay, CNC says it sounds good. My mouth is right close to the mic. Okay. All right, we'll keep going, and yeah, tell me if you think it's bad or good as we go, and I'll keep adjusting it. All right, so let's see. All right, so we're looking at the system clock. So so right here, this is the, I'm not going to really go into the clock part of it. I do a whole set of videos on just putting it into the 48 megahertz, but it's very straightforward, and it's enabling the high-speed internal clock, the HSI, and then it does some pre-scaling, or no, this is the, there's a special part of the let's see if I can go there, the I2C. So the I2C is that block diagram of the chip. All right, so if we go to, all right, where's the clock? Oh, clock configuration. This is the block diagram of the clock. Hopefully you can see that. Let me take off the, yeah, so this is the block diagram of the clock. And you can see the PLLCLK is here. So the only way to get 48 megahertz to be enabled is if you use the PLLCLK. And the PLLCLK has a multiplier here, so you can actually multiply it by 16 times. So just wanted to show that to you. We don't want to do any changes there. So we have the, let's see, what is it? Does it say what it's multiplied? Yeah, so multiplied by 12, which equals 48 megahertz. If you take the HSI and divide it by 2 and then multiply it by 12. So that's what that's doing. We're turning on the PLL clock section of the blocks, section of the circuit. I think the YouTube is way behind. Maybe not, I don't know. All right, so let me get this back to the other camera here. All right, so circuit and program. I'm going to see if I can change the, let's see what streaming I'm using or output. 6,000 kilobits per second, so that should be fine. Okay, so I'm getting a lot of freezing on YouTube from my end. Are you guys seeing any of that? I'm wondering if it's on my side or if it's my upload or download. All right, I'm gonna keep going. Oh, Twitch stream is down? It does look down, doesn't it? Okay, let me start it again. Actually, I stopped it, I think. Yeah, I'm gonna start it back. Okay, it should be online now, or getting online. Maybe that's a better place. All right, great. Okay. Yeah, I'm still getting the spinny circle on my YouTube. Okay, let me, how is this? I wasn't putting my face towards the mic before. All right, let me take a look at the audio capture. Okay, testing. Is this better, the sound? Maybe I should put my mouth away from the mic and just turn the mic gain up. Okay, so my tech is saying it's good. Okay. All right, so if it's good and there's no clipping, I guess that's a good thing. All right. Okay, so let's get back to this. So then I have no idea what this prefetch is, but I'm going to assume that that's a good thing. I've never used the flash before, so that's new to me. So generally, this is the stuff that's putting it into the 48 megahertz. So I guess this is, this is exactly what it says, latency. And I'm not sure. I think I had a version of this program where it didn't use this. And this was me trying to problem solve the issues. Hi, Bacteria. I hope I'm saying your name right. The compiler that I'm using is, well, it's the STM32 Cube IDE that uses the compiler. I haven't really delved into what, but if maybe you can get some information from this. If I do the play, I'm going to plug it in just to get something going here anyway. Okay, no device found. So that is because of this, and this is good that this happened, because when this is plugged in, or when this is powered, I should say. I'm going to try it again, because usually when I get that, it'll work. Okay, so no device found. So when this is powered and it's not working like it was not working before, it's not going to be able to find the target. And when it says target, it means the microcontroller. So if I move the power, I could also move the ground, but right now it's not being powered because it's just on a unused tie strip. I don't want it floating because it could hit something. So let's see if it works now. No. All right, so I'm going to have to unplug it and plug it back in, and also make sure everything is... It's kind of good that this is happening, because this is what gets most people frustrated. Okay, so after I moved that, because this was interfering with it, after I moved that and powered this down, it is working now. So you can see that it downloaded, verified successfully. So there's a lot of reasons why you were going to get the no target. I also have 2 other videos out there that talk about, like, if you accidentally program these 2 pins as general purpose output input, these are the programming pins. So if you accidentally do that, you have essentially bricked your microcontroller until you can do an erase. And let me show you the utility for that. So if you do somehow brick your chip, you can use this utility, and there's a little dynamite full chip erase. Use that to erase it, but you're going to have to, I would follow the video that I made in the series. Let me see if I can find that video, because it's a good video to know about. All right, so this is my channel here. On the home, you'll see a number of this stuff right here will give you sort of a quick link to several playlists that I think that will be very helpful. But it doesn't have the latest one. So there is one in here. So if I go into this one and I go how to resolve cannot connect to target, that's one of them. So look for this video if you can't connect to target. And let's go to the other video. This is under playlists, and it should be, yeah, here we go. I'm live streaming. Say hello. All right, so let's see, okay, right here, I think this is the one. So it says, I bricked my, let me see if I can get that more in, yeah. I bricked my ARM microcontroller, how to fix. So this shows you essentially using that same utility, using the chip erase, and you have to use the reset pin in conjunction with that utility to do the full chip erase. So that doesn't tell you what the compiler was. Sorry about that. But I think in here you can probably. So I don't look into all of that. So that's just something that I don't worry about. I worry more about programming and and getting the chip to work rather than the stuff in the background. Even though I like the low-level stuff, this is kind of low-level, but I don't really worry about that much. So I apologize for not being able to answer that question fully. ARM GCC, yeah, that's probably it. Yeah, that sounds right. I think I talk about that in one of my beginning videos way back 6 years ago, more than 6 years ago. I do actually install this. Yeah, I install the GCC, so that's it. You see, that stuff escapes me. I'm getting old, and live streaming just doesn't help with that either. So thank you, Gorzd. Appreciate that. I hope I'm pronouncing that name right. And welcome to the live stream. All right, so let's go back. All right, so this is essentially the what makes the microcontroller go at 48 megahertz. And just to review, this is probably not needed. More on the PL system clock, and you could also set it up with the I2C file. You can just do that just by clicking on those check boxes or radio buttons. Okay, so let's go to now the I2C initialization, and I'm gonna go to the reference manual and talk about what's in this I2C initialization. So let's go ahead and start with that. Oh, thank you. 99% better than Italians. That's funny. All right. So let me see if I can actually get something to display on here before I talk about that. So let's put something in here. It has to be all in caps, actually. And we'll get into that too. All right, so let's go ahead and run. Since we took this away, it should be able to connect. All right, that's good. All right, I'm going to disconnect it, put this back on the plus rail. That's plus, right? Yeah. And then reconnect it. Let's see if something displays. If something doesn't display, then I'm in trouble. All right, it's not going to display now because every time I plug it in from here, it doesn't work. So I have to kind of reset it. So I'm going to do that. And also, I want to investigate if I need those 4.7K resistors, pull-up resistors. Okay, it worked. So let me get closer in here. So you can see it says, hello everyone, exactly what I wanted it to say. One of the weird things about this particular display, I've had this display for years. Literally, I've had it for probably 5 years. And that's probably one of the reasons why I thought it didn't work anymore, because it was just so old, and maybe I carried it too many times, and maybe I caused some ESD or something. Yes, it is due to the font library, and I'll show you that in a little bit. It might be able to do lowercase. I just don't know yet, because what's available online is skimp, is very small. So yeah, we'll get into that. So everybody can see the hello everyone, right? Somebody tell me what I should be writing in here. What should display? And I'll try to display it. I'll do that on the next lines. And you'll see why what the weird thing is I'm talking about with this. I'm going to bring down the, oh my god. Okay, that's a little bit better, right? You can see that? Gorazd, the pull-ups are usually on the LCD itself. Interesting. That's really interesting. The short lines, and I'll take a look at that too. I'll look at it much closer to see what's on that board. So let's do that now, actually, right after I change the display on the LCD itself. For short lines in I2C, I set 100K. You can use internal pull-ups. I'm going to see if I am using the internal pull-ups in the program. So we're going to investigate that. And yeah, don't forget to like and subscribe if you haven't already. I think the number of people I have on my live streams are probably already subscribed, but yeah, good heated advice. All right. So what should I put in here? Like and subscribe. All right, so it will flash the microcontroller when I press the play button here. And that's because this is in a working state. For some reason, that's the way it works. I'm not sure why it's doing that. I think it's a power issue. But I've also checked to see when it's not working and it's not able to to upload the program. I've checked the power and the voltage is identical, so I'm not sure why it's doing that. So let's go ahead and... Oh yeah, you're right. The cursor. See what it did? That's the problem with latency in YouTube. I can't see the comments fast enough. Alright, so let's do it again. There you go. Alright, so that worked. And look, you see the top two lines? It's really hard to get a good view of this online. It looks more like this in real life, where it's more yellow and more blue. But when it's focused, it's like, it's kind of muted. But notice the top two lines are yellow and the next two lines are blue. In fact, the rest of the display is blue. And Robert, welcome. Thank you for joining. All right, so why is that? I'm thinking that the inventory that company had, they probably had it for a specific application. Like the top line had to be yellow. But if that's something that anybody knows about, let me know, because it's interesting. I don't know why that is. So, all right, let's continue on. And I'll keep this going as I show the program. Okay, so we were at I2C initialization. So let's take a look at that. It's probably going to be way at the top. And don't worry about all these functions and stuff. It's very, very easy to understand. And yeah, I want to talk about all these things, but I can't yet. Okay, so here's the I2C initialization function. So it runs all this code when it calls that function in the main area, the main function. So we're using GPIO B. Let me open that in Newbie Hack. Take the caps lock off. So the two pins that we're using is 58 and 59, and this is PB7 and PB6. So we need to enable the pins for port B. So that's what this is doing. It's using the real-time, the clock and control register. But is this I can't remember what the R is. I think that's real-time clock and control register, and this is the advanced high. Actually, I don't know. This is the advanced high bus. No, that's the APB is advanced high peripheral bus. This is the enable register. So this just happens to be in the enable register of that RCC, and we're using pin number 6 and pin number 7. So like we said before here. Hopefully you can see this. Pin number 6. It is kind of small, isn't it? Let me make it bigger. This is an SVG, so it's able to enlarge in itself. Okay, so PB7 and PB6. This is the clock, the SCL, and this is the data, the SDA. So 59 or PB7 is the data, and 6 is the clock. It's starting to rain a little bit harder here now. Right. All right. Taking a look outside to see how windy it is. Not too windy yet. The rain comes in little spurts, heavy spurts. Oh, you can hear the rain? That's interesting. When the wind blows really hard, I've been in about 5 hurricanes in my life because I lived in Houston as well. And I've been in one in Hollywood, Florida. I think 2 in Tampa and 1 in Houston, and maybe more actually. Hey Nicholas, Nicolas. Yeah, I decided to stay home, and not only that, but you decided to work with electricity during said hurricane. Yeah, well, if I get electrocuted, you guys can call 911 and live stream. That's true. Well, what is there to do? You know, I have lots of people in the house actually. I was talking about that in the beginning of the live stream. So I've got my sister and her better half, and 1, 2, 3, 4, 5. So 7 more people, my daughter and her friends. So that's about 10, and me, 11, my wife, 12. and my son sometimes, 13 and 14, and his girlfriend, and let's see, 3 dogs, my cat you saw in the beginning of this live stream, and 5 more cats because my sister brought her cats to be safe here. So this is kind of a shelter here, and I'm staying away from them so I can. It makes me anxious a little bit. I'm working on a Nicolas says I'm working on a vintage Harrison 855C power supply at the moment. Awesome. By the way, I didn't mean to sound mean at first. Oh, you didn't sound mean. No, I didn't take that as a mean statement at all. All right, so let's continue on. Yeah, no, I want to do something other than focus on the hurricane today. By the way, I have an update available. Oh, you can't see that. Huh, that's weird. Oh, I took it off, I guess. So I have an update for STM Studio, but I'm not going to run that right now. Okay, let's continue on. All right, so 6 and 7 on port B. So PB7 and PB6. 6 is the clock, 7 is the data. So what it's doing here is the mode R register. What it's doing is it's setting them up for the alternate function. So that's a special case for the mode register. Generally, with the mode register, if you're just doing input-output, you're just going to set this mode register. This is what you can set the pin for input. So like you can put a button there, or maybe an encoder or something like that. Or you can set it for output, like displaying an LED or sending data. You can create your own communication protocol using an output if you wanted to. And then you have the alternate functions. So let me see if I can find the alternate functions for these 2 pins. So you already saw that in this. So the alternate functions, you can see it says alternate right here. But the alternate functions are, this is the standard function. It's just PB. So it's general GPIO, general input output. That's the primary function of all of these pins. And then you have the alternate function, and you can make it do whatever you want it to do, as long as the pin has that as an available function. Can you add sensor data to the display, like the G-load sensor or temp? Yes, that's what I'm going to be doing over this series of video of these live streams. Is I'll eventually show data on the display from the 2000G accelerometer. So that will be the intent. It's just displaying like what I was showing in the last live stream, what was showing up in the STM Studio. Instead of using the STM Studio, I can show that data here instead. Hey, thank you for joining. Okay, so let's go and take a look at the alternate functions. So I'm going to look up the alternate functions for this chip. So let's see if I can find the alternate functions. I don't believe the alternate functions is listed in the reference manual. It may be, but I don't think it is, but there's a really convenient table in the data sheet of the STM32 F030 microcontroller. All right, so let's see what we get. So I typed in STM32 F030 datasheet. I might actually have it on my website. So this says F4, but it might be the same. This is from STM Micro, so maybe that's the one to look at. Documentation. All right, so we have, wait, let me make sure. Yeah, this is the F4. It might still be the correct one, or good enough. Hey, thanks CNC. I appreciate the $5. Very kind of you. All right. Yeah, can you hear the rain? I can't believe you guys can hear the rain. This microphone picks up quite a bit. I thought it was you had to be pretty close to the microphone to be able to hear it. All right. Let's see. What am I looking for? This is the reference manual. the device errata, application notes, presentations, flyers, brochures. It doesn't have the datasheet. So you're looking out your own window. That's funny. Yeah, this is a more calming live stream. All right, so I'm going to look somewhere else for the 96 pages. This looks like the one that I need. This is the C8T6. I'm using the R8T6, but these are going to be identical. Or not identical, but they'll be very similar. All right, did it download? Oh no, I have to use this. All right, let me see if I can find another one. Mouser, F4P6. Okay, this is probably the one. Okay, here we go. All right, yeah, this is the one that I'm looking for. So let me make this a little bit bigger for you. Huh. And in here should have the alternate functions. See if I can use the F for port B. Okay, here we go. So this is the reason why I use the datasheet, because it shows exactly what alternate function is used for each pin. So in the PB6 you can see that I2C1 SCL and I2C1 SDA for 7. So these are the two that we're using. And you can see that it's AF1. So this is an important designation here. It's AF1 for both of them. So for 6 and 7, AF1. So when we go to the reference manual and determine how we set that, we would need to know which AF we're using, which number alternate function we're using. All right, so I'm going to get rid of these. I'll keep this open just in case I need to look at it again. But let's see what it's doing here. Let's go to the reference manual. And I have it, I believe, on my website somewhere. Yeah, so you'll know where to look for it. It should be on this page actually. Okay, yeah. Well, look at that. I have the data sheet as well. So you can just click this to get the reference manual. Let's see if it still works, because ST Micro tends to change links sometimes. Okay, it does work. So go ahead and download this if you need the reference manual very conveniently on this website, and just press ARM, and the data sheet's right here as well. Okay, and you also get the SVG here to look at for convenience. Okay, all right, so let's go ahead and I'll go ahead and just download it again. It's not like it takes much room. It's only 700 pages. Okay, so we're looking at the mode register for GPIO. So let's go ahead and look for that. I want to change what's on the display. So does anybody have any suggestions on what I should change it to while I look for this? So this is the GPIO, and the registers here, this is the mode register. All right, let's take a look at the character set. So actually, just before we do that, these are the characters. So we have the space, we have some general characters, we have the numbers, and we have the letters. So give me a message I should put on there. Rain, rain. Okay, there we go. Let's do that. I wonder if I can do the smiley face. I should be able to. Does it have the colon in there? Yep, the colon's here. And the parentheses. Yeah, that's there. All right. All right, let's go ahead and program the microcontroller. Chocolate Rain. I remember that, those videos he made. What's the name of that YouTuber? Oh, look at that. It went to the next line. That's interesting. I didn't know it would do that. Wait, I'm going to put Chocolate Rain on the next line. 4. Oh, wait, let's make this an empty line. So let's go 5. I love that song, by the way, Chocolate Rain. Yeah, I looked him up not too long ago. All right, let's go ahead and update. Let's see if I can get a better. It's really hard to get a good. Here we go. Chocolate Rain. It's difficult to get a good focus on that. Can you hear the rain? It's pouring now. In a little bit, I'll give you a shot of the outside. It is coming down. Okay. All right. So back to the mode register. Where was I? Here. Okay. So the mode register, you can see that for 6 and 7, there's 2 bits, and for the alternate function, you need the bit number 1, which is this one right here. Bit number 1. You need that to be a. Oh, I can't just select that one. You need that to be a 1, which is this bit here and this bit right here. because you can see the 1 is here and the 0 is here. So if you have trouble reading reference manuals and data sheets, it's good to look at this, the way it shows. So you know this is bit number 1 and this is bit number 0. So that's why it's showing, let me go back up to that. That's why it's showing only the 1 being set, and it has an AND, it has the OR bitwise operation, which just puts a 1 in those bits. But this is not good programming practice. You also want to make sure that there's a 0 on those other bits. So we're using the AND bitwise operation and the NOT. Actually, I want to do this. I think this will work. So we're knotting these, and we're using the AND bitwise operation to make that work. This is essentially a mask, and in my videos I talk about what masks are. Oblivion 11, hi, welcome. I have an issue in Flash. Could you help me find the question? What are you having a problem with in Flash? And Flash meaning the microcontroller flash memory where you put the program, or storing stuff for non-volatile memory use. Okay, so all right, so now we're putting a 0. We want to make sure that this is a 0 here, and this is a 0 as well. And the reason why we want to make sure that we put a 0 on those bits is because if we didn't, and this was set as a 1 somewhere else, because programs get really large and you may not know that you've done that, and you might want to change the mode for some reason on those 2 bits or those 2 pins, you'd be in analog mode. You wouldn't actually be in, I don't like when that happens. So you'd be in analog mode, not in the alternate function mode. So you want to be careful with that. So that explains this. We're setting it up for alternate function mode. The O type R register, the output type register. Let's take. So the output type register is the next one. So what we're doing is let's see what it's set at and see what it's trying to do. So right now it's being set as a 1. So 1 means open drain. That means it's not going to be using an internal pull-up resistor. So this is a good time to take a look at the circuitry on the back of this display. All right, Oblivion. The STM32 Cube IDE says cannot find the target. Okay. When I first time to do the LED, when you first do the LED test, and I followed your video, but it still doesn't work. In this video, I talked a little bit about not finding a target. In fact, it actually happened while I was doing it in this video. So what I would suggest is, so in this video, I wasn't able to flash the microcontroller because it said the exact same thing you're talking about, you're saying. And I had to turn this off, essentially unplug the power for this display. And then it worked. But I also had to make sure that I unplugged the programmer and then plugged it back in. So it kind of reset it. So that's one of the issues. One of the other issues could be that you've programmed these two programming pins by accident. And you'll have to do a full chip erase. And I talked about that a little bit also in this live stream. I don't want to get too far into it, but you'll want to use this utility here and the full chip erase. And you'll also want to, while you're doing that, reset the reset pin at the same time. And in my earlier videos, I show how to do that. So take a look at that, and if that doesn't help, let me know in the next live stream, or because it'll take a little bit of time to figure that out. Also, just take a look at the board. Make sure there's no bridges or anything like that, or if you've accidentally done an ESD or static electricity on the board, that can also affect that. Because One thing to note about single chip microcontroller setups like this, one of the unfortunate aspects of that is that there's no other circuitry to absorb a lot of that static electricity. So sometimes, like in circuits, they're less susceptible to ESD than something that's just like a single chip like this that has no protection at all. This is sort of more delicate, so you want to make sure that you handle these chips or these boards a little bit more cautiously, and maybe even using a ground strap when you're using it. So there could be a few things that's few issues. It is really coming down now. Yeah, it's now a constant pour of rain. All right, let's go back. So the output type register is being used as a open drain. So this tells you that we're not using a pull-up resistor internally. So internally we can actually take these two pins and apply a pull-up resistor of a value that I do not know to the. You can pull it up or pull it down. You can pull it up to positive voltage, or you can pull it down to ground using resistive. But it's nice to have that as a feature in the microcontroller. But in this case, we're doing open drain. So let's take a look at this display on the back of it and see if it does have a resistor to those pins. Let me up the ISO a little bit. These pins here, and I do see resistors. So I don't know what the values of these resistors are, but wait, does it say that actually here? I may say it. Let me go a little bit closer. It says 24.7 by, okay, so that's not it. Okay, so I'm going to take a multimeter and test the resistance of those resistors to see, are these resistors? They have a value on the top, it looks like. Let me get a better view. That's a very strange letter on the top of that. Oh, I can't really see. It looks like O, which is kind of an odd number to be on a resistor, but it could be too small for a number to be painted on there. 0 ohm. If it is, that'll be interesting. All right, so let me go ahead and get a multimeter and see what that is. It's 7 mega ohm. That's weird. Same with this one. This is 7.57 mega ohm. So these are not the pull-up resistors, so maybe it's over here. There's two other resistors on this side, and I can't really see the number on that. It looks like 103 or something like that, or 101. These are standard, like, what is this, 10K maybe? Or 1K? This one is too. Yeah, it's not reading at all. Oh no, it is. This is a 10K. Yeah, it's a 10K resistor. Okay, so 10K seems about right, because 4.7K is what's generally recommended for I2C. I believe that I used 10K in my previous projects 6 years ago. You'll see that on the video. So these are probably the pull-up resistors. So that's why I don't really need pull-up resistors. So you're right. Yeah, I need sharper probes for sure. And there's probably some residue on top of it or something. So those are probably the two pull-up resistors. I might be able to, let's see. The SDA pin is right here. So I could probably just probe the SDA pin and one side of the resistor. Yeah. So that's connected to SDA right here. And I'm guessing this one is SCK. Yeah. Wait. Yeah, that's to the SCK. So this is the SDA resistor, and this is the SCK resistor. This should connect to the power, so that would be the third pin here. I got 2.7 mega ohms, 3 mega ohms. That's weird. Unless this, no, this is ground. 0.4 mega ohms. Well, one would think that this would be pulled straight up to the positive pin, but it shows 2.96 mega ohms, so I'm not sure what's going on there. But this, I think this is probably the pull-up resistors. I'm probably not measuring it correctly. All right. Spam. Okay. So we know that there are resistors on the board. So whoever mentioned that before, I think it may have been Skeptic. You're right. All right. So that's why I really don't need the resistors in the circuit. So let's see if I can get this back on there correctly. Does that look right? Yeah. Okay. Let's see if it still works. All right, so right now you can see that it didn't show up. I will not be able to do a successful flashing of the microcontroller. So if I tried to press this, you'll see that it will say target no device found. So Oblivion, this one is for you. Error in initializing ST-Link device. Reason no device found on target. So this means that it found the programmer. It found the device that flashes the microcontroller, but it didn't find the target itself, the actual microcontroller itself. If I reset, and then now you can see what's shown there, it will work. Something is going on in behind the scenes or internally in the circuit that, or maybe even the programmer, that it fails on that in that way. So if I do a reprogram, it should program. If it doesn't, then I have to take out the, so it did work. But if it didn't work that time, I would just take the power away from this. Or if it still didn't work, I would just remove this entire circuit completely to make sure that I would be able to program it. But I've never seen that kind of, I've never experienced that before, so I don't think you'd have to worry about that. My car's extended warranty. Yes. All right. That's a running joke, a meme, right? So that's why the type register, and this is the way I used to do it, or I did it in my previous videos. I set it to open drain. So it's acting as if it's an open drain transistor. Yeah, transistor. Okay, so now for the speed. Let's see what speed it's setting the pins. So looks like it's making it a 1 for each of those speed bits. So in the speed register, it looks like it has 2 bits. That's interesting. Oh, so it is, wait. Yeah, when you don't use the -1 or -0, it'll probably put an 11 there, or 1-1, not 11, but it's 1-1. In binary, that would not be 11, so. Okay, so it's setting high speed. So it's ORing both of those numbers at the same time. Oh yeah, Skeptic, I talked about this earlier. This is a, I'll give you a really quick rundown of what I did, how I found this. Since there is extremely limited information on getting this display to work, I used Claude. Now what I'm doing is I am deciphering what Claude gave me so I can use it and make it because I didn't want to use any libraries. Pretty much every example out there on the internet uses examples or uses libraries for this display. I don't want to use libraries. I want to find out how this display works and what goes into the addresses, what addresses you need to send to it to make it work. So yeah, I'm using Claude's program, and if you looked through the internet, you may not be able to find any of this. And also, I talked about in the beginning of this live stream that the datasheet for this display is just not available. I cannot find the datasheet. There is one datasheet available, but it's making it work through data pins rather than the I2C. Although in the datasheet it does make reference to the SDA pins, but the addresses are not shown for the internal registers for the The display, it doesn't share that information. It only shows how to communicate it through the 8 data lines, the 0 through 7 data lines, it's kind of frustrating. And I'm sure it's out there because if Claude knows about it, then it should be out there somewhere. I just don't know where it is. So this is me sort of cheating a little bit, finding the information and understanding what Claude is giving me, so I can either make it better, understand it so I can make programs for other I2C devices. So it's kind of a learning opportunity. Yeah, I'll put it in the chat. It's the GEME 12864-54, and there's also a 43-43 that's displayed on this portion. You can see it really, it's difficult to see it, but you can see that 43 there. So that, I think, is the actual display itself. So that's an SDI something or other. But and also you might be able to find a data sheet if you wanted to just use those data lines instead of using the I2C. Okay. All right. So Oblivion. I was following the solved video, and when I do a 10K resistor on the pin 60, connect to positive, the circuit is not working and the ST-Link V2 light is off, so that I cannot do the erase. Keep trying, but you also have to make sure you're disconnecting the ST-Link and then reconnecting it again. If it doesn't work over multiple trials, that chip may have been blown or from static electricity, or maybe there's some bridges on there. So, take a microscope if you have it. Take a look at all those pins. Make sure there's no bridging on the pins. Yeah, that's all I can think at this point. You could also look at the run configurations and take a look at some of the values in here, the debugger, and just look at some of the stuff here. If you're not able to erase, then this is not going to help you anyway, but this could be something that you look at if you do get it to erase. But if you can't get it to erase, that's a sign that and using the reset pin, it may not, and also make sure that the chip is soldered on there in the right orientation. I may have made a mistake and put it in the wrong orientation. So I do these all by hand, and maybe I'll mess up once or twice per 1,000, 100, I don't know. So yeah, take a look at the, make sure that small circle on the chip is at pin number 1. The large circle should be facing the skull. So the large circle should be on this side, and the small circle should be on that side. See if I can get a close-up view of that. You can see that big circle is next to the skull, near the skull, and the small circle. It's hard to see the small circle, but that's the small circle is the pin number 1 circle. It's probably the lighting in here. You can see it a little bit. It's a little bit of a concave circle. Okay, let's continue on. So we're looking at the type. We have an open drain. The speed is a fast speed. I put on slow speed on my previous I2C videos, but I was able to, I think, get this to working at 1 megahertz, which is really fast. You can see if I slowed it down, you could see this actually form on the screen from top to bottom. All right, so now the pull up, pull down, it should say no pull up. So that means because we're using open drain, we can't use the pull ups anyway. So let's take a look at that part of the data sheet. So the pull up, pull down, no pull up is 0, 0. And it should be for 6 and 7. So let's take a look at the program again. So here we go. It is, yeah. Oh, so this is interesting. I like the way that it's doing it there. Let me do that here. Actually. Okay, so it's putting a 0 in all 4 of those bits. 2 for the 6 and 2 for the 7. So, and I just updated this one, so it also puts those bits 0, making them 0. All right. And it still worked. So I did it. I did run it even that way with the and here. And all right, take this space out. Okay, so this is generally a GPIO type thing. So, but it's because it's putting it in the alternate function of I2C, it put it into a I2C init. So let's take a look at, this is where you're setting the alternate functions. So I did this a little bit differently in my video, where I believe this one is for 24 and this one is 28. So let's take a look and see what the actual, or 44 and 48. 24 is the, yeah, 24. And then this one should be 28. 28, exactly. So that is correct. So what it's doing is it's putting a 1, and let me draw this out here. So as let's make it a 32-bit number, 0B, and 32 zeros. Okay, that should be 32. So a left shift, a 1 here, would put a 1 shifting 24 places here. So let's see what that would be. 1, 2, 3, 4, 24. I think it's this one here, and then over here would be 28. So 24, 25, 26, 27, 28. So that's what this number will be once this, well, that's this number here. So this is essentially creating this number here. So it's just putting a 1 here and a 1 here. Okay, so those are the alternate functions that we needed to work. So let's go to the alternate function. Okay, so the AFRL, and you notice that it had a 0. So that's just the specific table that we're going to be using. So you see there's multiple tables. Wait, no, there's two. Yeah, there's two tables. So there's one, there's a 1 and a 0. So this is the high register and this is the low register. So we can see the AF4. I think it was the AF4. Wait, what was it, the AF1? I think it was the AF1 we were looking at. I can't remember actually. It's the AF. Yeah, it's the AF1. Okay, so the AF1 for 6 and 7. So you can see right here, number 24. Let me go ahead and make that yellow. This is going to need to be a 1. And for 7, number 28 needs to be a 1. So it would be 0. So like right here, it would be 0, 0, 0, 1. And on this one would be 0, 0, 0, 1. So we're using that feature for the alternate function. So is that clear as mud? Skeptic. One thing you can do is find out what driver chip it uses. Just like the normal LCD, you can find the datasheet for it. I found this driver, for example, SS. Yes, I found that too, but it still didn't show me the addresses. Did you find the addresses that it shows? Let's see. Like right here, these addresses. What I'm looking for a document that shows all of these addresses and also shows me these address combinations to create these characters. Because the one that I have, and I'll show you that one, not that. Let's see. Yeah, right here. This is the one that I found, but it shows communicating via data pins, just like you would do with an LCD. And I'm looking for the data sheet that has those addresses instead. Oh, nice. Okay. Oh my God, you hear that? Let me show you what's going on with Milton. You can't even see outside the window. Let me see if I can get a better focus. That's my crepe myrtle. All right. As I explain the program, I guess I can keep that on. All right. Let's get back to it. All right, I'm going to look up that SSD1306 PDF. Let's go take a look. Oh, nice. It has a command table. That's awesome. The Adafruit, that one's probably a pretty good one. They usually have a really good library of data sheets. They started 2 years before I started their company. They started 2005. I just looked that up. It's pretty cool. I love their company. All right, let's take a look. Yep, this is definitely 128 by 64. Let's see what they have in their data sheet. Let's take a look at the features here. This is a very well-made data sheet. The other one I had was, it's essentially, this is text, but over here, this is just an image. All right, so let's see. Okay, so VDD can go up to 3.3. I think this is just for the display because I know I can go 5 volts on it. So these, yeah. So these are the data pins I was looking at before. You have VDD, VCC, VSS, and LSS, and this is, let's see, they don't have the pins of the I2C, but let's keep looking. I think there is some circuitry on my board that allows it to go up to 5.5 volts. I2C interface. It's good that it shows this. And this is SPI too. So I guess you could also use those pins for SPI, like master out slave in, master in slave out. That would be, you'd still need a clock source, I think. So I don't think that they would have those number of pins. So maybe not, but definitely I2C. All right, so let's go back to the datasheet. This looks like a different size LCD, or maybe this is not the, this is maybe just the IC portion of it. All right, what is this? Oh, okay, coordinates. Wow, lots of information. Okay, the scary amount of information. So this is the little ribbon cable I showed you earlier, and the pinout of that ribbon cable. Oh, too late. I'll probably take that out after the live stream's done. Did it show the IP or the IP address on the speed test? Okay, let's see. This is still that ribbon cable information. Okay, this still looks like an LCD type communication here. Let's keep on trucking. Yeah, this is still data stuff, data pin stuff. Okay, so this is the I2C interface. So I could have used this in also in Claude to help me out, but SA0 is the slave address, bit SA0. So yeah, so read write bit. I went over this in my previous I2C. So you have the data, and then a read write is the first digit. So you have to left align the data and then reserve this for the read write. Let's see. So it does give information on the I2C. That's good. So when I go farther into the I2C setup, I can look at this. Let's see what speeds it allows. Because I think I got it running at 1 megahertz. Usually they're like 100 kilohertz to 400 kilohertz, but this seems to be a little bit faster. All right. Okay, so this is communication. You have the acknowledge, data byte, acknowledge, control byte. I don't know what this is. Another acknowledge, data byte, control byte, read write, and this is the data, and then the address. Oh, that's the slave address here. So this is the slave address. Is it actually the slave address? And it would be interesting to see if you could do 2. I'd have to see how the IDs work. All right, cool. Thanks for that. On 28, let's go take a look real quick. Where's the page number? Oh, here it is. Okay. Yeah, no, this is what I had on the other one too. But where's the address? That's the problem. Oh, wait. Are these the addresses? Let's see if it coincides. So if I was gonna, let's see, what would be set memory addressing mode? Display off. AE would be display off. Wait, what was that again? Was it AE or A0? AE. I think I passed it actually. Or did I? No, it's A3. Yeah. I'm probably not reading this right. This may not be the same address. So let's see. Let's look for display off. D3. Is there any other information? Yeah, it is AE, but where do you find that in the data? Or is this D3 left shifted with the read write bit? Last row of the first table. Oh, here we go. There. Ha! Okay, cool. Thank you. Yeah, it could take a little while to find things. It definitely takes me a little while. Okay. It's past 4 o'clock, but I think I'm going to keep going. All right, so that we know. All right, so we can take a look, and we could verify this, but I'm sure it's working right. I'm using horizontal addressing mode, and what does that mean? That would be 00. Yeah, it definitely takes time for sure. Doing it on a live stream, probably not the best way to do it, but you can at least see the way I'm thinking, and with the help of you guys, that's definitely is a lot better. All right, so what was I looking at? Well, I kind of want to look at what they offer as in features. Oh wait, hold on a second. This stuff here, character creation, I don't think it would have that, but I could be wrong. Oh wait, what is this? Set display offset. Maybe what I do is I go over this datasheet offline later on, and I just continue with the I2C stuff. So this is the, I guess, yeah. So yeah, this is the chip it's using. Just like the LCD, that's how you look up the datasheet. Is you look at the chip that drives the datasheet, the display. All right, so I'll look at this later. I am kind of curious to see if there's any character stuff here. Really quickly, pin information. This is really good stuff here for communication. If we wanted to put a logic analyzer on it, we can use this part right here to confirm that we're, bringing the levels high and low correctly. Okay. All right, that's it. All right, so I will keep that in mind. It's already saved, so I got that. All right, let's go back to the program. So we were still on the I2C. So we got that. We stopped here at the alternate functions. So now we're going to be enabling the I2C clocks. I don't think I did this in. Oh, this is just the enable. Actually, you're just enabling the I2C with this one. So let's take a look at the clock control register. Do I have the programmer's reference manual open? Yes. Clock and control register. Here we go. And which one was it? APB, Advanced Peripheral Bus. Probably this one here. I2C. That's not that one. Oh, it's probably this one right here. Let's see. Yes. Okay. I2C. So this is enabling the I2C essentially. It's the clock enable. So that's just this is the first line for I2C, and the system configuration. That's the number 2. Let's see what that does, because I don't know what that does. That's this right here. So this is the system configuration clock enable or disabled. So that's weird that it put it in that area. The system. I want to read more about this actually. "43 instances of it." Okay, interesting. So maybe it works with the I2C, because I didn't use this in my other programs, I2C programs. And I'm curious if it's important or not. Which one is it actually? Let's see. Sys, I guess config gen, CFG. Huh. Let's keep going up a little bit here. Oh, there's 92 instances of it. Ouch. And this is the configuration of it. Ay. No, it won't find that. It won't find the actual bit. Okay, so it just shows that as the. Oh, it has 2. So let's see if there's another. Okay, that's it. All right, so I would have to. I'm probably going to have to read up a little bit more about that, but I'm not sure why it's using that. But it may be a requirement in this particular case. This is the. Okay, there's a lot of instances of this. As you can see on this area right here, you can see where it's being used. This is generally the area that I'm in right now. So it should have more information in this section. I'll probably look at this offline. Here we go. This might be helpful. Okay, here is embedded bootloader. Huh. In the boot mode. So this is interesting. I've never really worked with boot mode stuff. I'm going to keep this line in. I may take it out just to see if it really affects it, but I don't really know anything about that bit. So that could be a subject for maybe a later live stream. But I'm going to put a note in here. In fact, you know what I can do? I have it in caps. I'm going to ask Claude. Oh, we know this. We know this. Okay, so this is a bit mask. Obviously, it's a bit mask. Okay, so that doesn't tell me anything. Enables the clock for the sysconfig peripheral by setting the corresponding bit in the. Okay. Is often used for remapping of pins, including I2C pins. Enabling the. No, the clock enabling step is typically part of the initialization process. Okay, so it's typically part of the initialization process, setting up the I2C communication. Okay, so it doesn't tell you what it's used for, though. Maybe it is the reason why the target wasn't found, because of the boot sequence. So maybe taking it out could make it better. I don't know. Let's continue on with this. This is kind of interesting. And ensures that the CFG proper operation. Yes, I would like you to elaborate. What would happen if I didn't use it? All right, let me see if I can get this all in the screen here. Okay, so the peripheral inactive, the system configuration controller, peripheral would remain unpowered and inactive. This is because the peripheral clock would not be enabled. Pin remapping issues. If your I2C implementation relies on non-default pins, which I'm using default pins, and requires remapping, this functionality would not work. This is really interesting. So the alternate function of the I2C can be remapped. That's interesting to know, if it can. The sysconfig controller, system configuration controller peripheral is responsible for pin remapping on many STM32 microcontrollers, including the, so it includes it. I'm not gonna trust what it says, but it says that I could with this. So like, say if I wanted to remap the PWM pins, would I be able to do that? That's an interesting concept, an idea, because in a lot of cases what I would do is, if I don't have the availability of that pin, like a PWM, if I'm using it for something else, I would bit bang that that pin to do what I wanted it to do programmatically. So that would be an interesting feature. Yeah, I'm definitely going to comment it out. Let's do that now that we're thinking about it. All right, let me bring the camera back. Do you guys like looking at the tree or the circuit? Because I can keep putting it back and forth if you want. Now we need to adjust my ISO. 1 second here. All right, that should work. I'm gonna try to give you a better overall view here. Okay, I'm gonna go ahead and run it. I think it's gonna work because I don't even know what that means. And I've done I2C before, so okay, it still works. Let me, because the problem that I was having before was when I was unplugging it and then plugging it back in, I couldn't get it to work until I reset it. So let's see if that has any. I'm not going to be able to show all of that, so I'll just bring this over here. I'm going to unplug the programmer, plug it back in, and it would not work. Let's see if it works now. No, it still doesn't work. So if I reset it, or if I unplug it here, plug it back in, it works. Every single time it will work in that case. So in circuit, without the programmer obviously, in circuit on a end user circuit, it'll work fine just turning it on. But for some reason, when I'm unplugging it from here, something happens in the boot sequence to make it not work. So should I go back to the trees or keep it? All right, let's get back to the, so I'm gonna keep, should I comment it out, keep it commented out, or I'm gonna keep it in, because this will be good, something good to research and understand more fully. But let me look and see read it a little bit more. Okay, so we're not remapping any pins. Potential I2C malfunction. Depending on your specific setup, the I2C communication might not work correctly or at all. This is especially true if you're using remapped pins for I2C. Okay, so we're not using remapped pins. So we know that it will work without it being used. So that is something that you'll see when you're querying or prompting Claude or ChatGPT. You'll see those kinds of things in there that you may not know, and it's good to look at, to research and see what it actually does. You know, we'll probably get to a point in time where, you know, AGI will happen and there will be super intelligence, and if you just ask it to do something and it does it, can you trust everything that it gives you? Can you trust all the output that it gives you? Right now you can't trust it because It's not always correct, but it's not necessarily nefarious. All right. Claude costs $20 a month. So does ChatGPT. So I'm using both of them because I do a lot of testing with both of them, and I kind of put them head to head. I pay for both services. Okay. So certain timer trigger remapping. Oh crap! Somebody just changed my TV. Okay, I'm back. My TV decided to go to Disney or Discovery Plus. Hold on one second. I have to use the restroom. All right, I'm back. All right. Skeptic. I use ChatGPT. I learn a lot, especially in C#, but I don't think they are that good for microcontrollers. I've found Claude is really good with microcontrollers, not necessarily ChatGPT. But if you're having some trouble understanding something specific in a microcontroller, it's a good resource, at least to understand it a little bit better. Right, unless it's a specific thing. What I used to do in when I was learning how to program microcontrollers, I would often just go straight to the programming examples. So it tries to tell you in the datasheet how to operate a device or a feature of the microcontroller. And with the examples and the explanation, because there's a lot of pitfalls and there's a lot of conditions that you need to meet, and it tells you that in the text, but this is also, it brings you up to speed pretty quickly on understanding how to program something, because you could take this program, say, this portion right here, and look and see why it's doing it in this sequence, and it'll tell you that in text up in that when it explains that feature. And like if you want to do something specific, you have to include this bit or whatever. And this is essentially how I learned how to program microcontrollers. All right, let's go back to the IDE here. All right, so now it's going to, I don't know what this one is either, actually. So let's take a look at what this one is. I2C reset. A reset. Is that a reset? Let's see. Yeah, it says reset I2C. I don't use this one either, so I'm assuming that it would automatically be reset when it powers on. So I'm going to comment these out and see what happens. And why is it... Wait, hold on a second. These are the identical lines. Why did it give me the... Wait, is this identical? Oh, no. One is... Oh, okay. So it's putting a 1 in that and then putting a 0. So it's resetting it. Maybe it put this in because I was complaining it wasn't working. So I was asking it to reset it. So let's see if it still works. I'm going to leave this out and probably leave this one out too, because this may have been it trying to help me be more robust of a program to make it work through the problems I was having with power. So let's see if this still works. I'm going to change what's on the display as well. So if there's any suggestions out there, yep, still works. Let me know what you'd like to see displayed. Yeah, exactly. I think what I would like to, because it's better to really understand a more simplistic version of this. So I'm going to remove that. And I like, if you've watched my videos, I like to erase all of the comments that it provides you. I don't like having guidance in that way. All right, so let's see what else. Okay, so this is the timing. This is pretty important because this will set it for the 100 kilohertz or 400 kilohertz or the 1 megahertz. So we can see pre-scaling is 0. We can look up all of these, but the best way to determine this number is through an Excel spreadsheet that STMicro provides. And that spreadsheet is, what is that spreadsheet? I think I wrote it down. It's AN4235. So I'm going to put this in here so you guys can see that. And in later live, if you ever want to go back to this live stream, you can take a look at it. So ST, I would say for speed or frequency. The document is AN4235. So 4235. My 3 is not working very well. So AN4235 is the Excel spreadsheet you can go to and take a look at the. It gives you some fields to enter what speed you want and whatever, and it'll give you these values. It won't actually give you these values. It'll give you the entire number, the bit, the byte that you can put in here. So I believe this is working in 1 megahertz. I don't actually know, but let's take a look and see. I don't have that much experience with this because I did use the Excel spreadsheet. It's just a lot easier to do than understanding all of these values here. But let's take a look and see if there's any. The spreadsheet provides the number. So when you use that spreadsheet, just expect a number like this to appear. So let's go up to the where it really explains it. It may actually tell you the spreadsheet too to look at. So that's where it's located here, and there's not too many instances of it. Okay, here we go. All right, so yeah, these are the specific, like this prescaler, the SCL. I don't know what that is. SCL, DEL, data setup time, data hold time. SDA is data hold time. SCL, this is data setup time, and this is essentially forming your timing diagram. See, and let's take a look at this one, which is very bad. It would be forming this diagram essentially. So the SCL high period time, the SCL low period time. So it's just adjusting all of those values. So we probably have very low values, so it's pretty tight. The timing diagram is going to be really tight. So it's the fastest it can be. So if we're running 48 megahertz and we are using the I2C at 1 megahertz, but that's multiplied by the reads and writes, because you have to specify, the slave address every time and state that you want to do something or whatever you want to do, like reading, writing, or whatever. That takes a lot of space there. So you're actually running like maybe 3 or 4 times or times slower. Yeah, 3 or 4 times slower. All right. So yeah, just use the spreadsheet for this. All right, so let's take a look at what this one is, because I know what the PE is, but I don't think I've used the ANF off. So let's take a look and see what this is. This is just enabling the I2C. So let's look. So let's take a look at both of them, just so that can be understood. Wait, what register is that located in? Okay, here we go. So just for information, the PE probably means peripheral enable, I'm thinking. Yeah, peripheral probably, right? Oh, it just equals. So they're overwriting the entire CR1. So let's see why that's happening. So they're putting zeros on everything but the PE and the AN. Let's see what that one is first, and then let's see why we don't need any of that other stuff. So analog noise filter off. So we're not, why are we even using an analog noise filter? Okay, so it's disabled. By putting a 1 here, we're disabling noise filter. I wonder what would happen if I had it enabled. Oh, it's windy outside now. All right, so if I didn't use this at all, let's see what would happen. So I would be using noise filtering. I'm thinking the noise filtering is going to take time, so it would need to run slower to be able to do that. So let's see if it still works if I do this. So I'm going to go ahead and run. Oh yeah, that's some high winds, and it still works. So even though it's at very high timing, this still works without this being on. But I'm more curious why they're turning other things off. So let's see if anything else is important. Okay, so calculation enabled, disabled. I don't know anything about that. Okay, so if no. So I'd have to read up more about that. The SMB alert, bus alert enable. What's up?
Wonder what you're doing.
Okay. Okay, so the bus enable, I'd have to look that one up. I don't think I'm doing anything there. The host bus address enable, general call enable. Okay, so this is changing the way it does the NAC and ACK. Acknowledge and not acknowledge. So it's disabled. The general call is disabled. The address is NACed. Okay. Clock stretching disable. Clock stretching enabled. So it's enabling the clock stretching. And I have no idea what this is either, but it's not really affecting anything. Disables clock stretching in slave mode. I think I may talk about this in my previous I2C, because I did watch the video today, and I remember me talking about this. I just can't remember what it is. It must be cleared in master mode. Okay, so we are using it in master mode. Slave byte control, we are making sure that the slave byte control is disabled. Okay, whatever that is. DMA mode is disabled. Okay, so we're not using DMA mode. And that's the receive. And transmit DMA mode is disabled as well. Digital noise filter. So I guess if we are enabling the noise filter, we would want to do something in here. So we would want to create some kind of noise. And since we're not having any problems in our setup, I'm not going to worry about this. But this is interesting to know that we have that feature. Error detection interrupt is disabled. The transfer complete interrupt is disabled. Okay, so we're not using interrupts, so yeah, that's fine. Okay, so yeah, this is, I mean, it's just keeping the defaults except for that one. And these, like the RXIE, TXIE, these are interrupts, so we're not using interrupts anyway. All right. Okay, so this is enabling fast mode plus. So we are sysconfig. So is this related to this? So we are using the sysconfig. So I guess we're using it in a way that allows a fast mode plus. Okay. I know what this is. All right. So if you're wanting to use something more than 400 kilohertz, you need to use fast mode plus. So that's what we're doing here. So I'm going to re-enable this because I'm thinking this is related to this part right here. So this is important, and I'm glad I found that. So let's go ahead and look at the sysconfig and the configuration one. Let's see, where would it be located? I want to go to that configuration register 1. Okay, this is number 2, and where's number 1? You'd think it would be right next to configuration number 2. Okay, here we go. All right, so we have... all right, let's see what this says first. This register is used for specific configurations of memory and DMA requests. Remap and to control special I/O features. Nothing for the I2C. So let's see I2C here. Fast mode plus. Okay, so we're enabling fast mode plus. So we definitely need to do the enabling here. So mystery solved with this. And Claude didn't give me good information on. Let's see. Did it say fast mode plus on this? Okay, so it looks like it is a prerequisite for doing the fast mode plus. Okay, good to know. So let's take a look at it's PB6 and PB7. So the fast mode plus. Okay, so it looks like you don't have the actual numbers in here, but so the fast mode plus from here to here. Oh no, actually to here. So PB, okay, here it is. See, PB 6 and 7. So it's these two here. It's these two bits that enable the fast mode plus for 6 and 7. Okay, good to know. Okay. So now we're enabling error interrupts. So it looks like it is now enabling something that was disabled up here. So this could be added to on the control register 1. Nothing else is on control register 1. So the ERRIE is enabling the error interrupts. So if there were any errors, I could create an interrupt function to to see what happened during that error. All right, it is 5 o'clock. I'm going to end it here. If you guys have any questions, I might leave the stream going for a little bit, just so YouTube is able to capture the end of the stream. So if you have any questions, let me know. Today is Wednesday, I think. So I will be working on CNC stuff tomorrow, live stream. I might be. Thank you, Sergio. I might be. Hopefully we'll weather the storm over here. So I hope you come tomorrow to check out some shielding stuff. But I also have a video that I haven't shown on YouTube, and it's from a while back, about the cooling system I have for CO2 laser and the spindle, and how I have that set up on the Fabricator Pro. And it's an old video, but it's a really good video, and I want to do some voiceover on it on a live stream to explain it. And I'll probably do that for maybe the very first part of the live stream, but then I'll get into the shielding portion of it, so I can continue the shielding session number 2 for shielding. So I hope to see you guys there, and I'm going to turn it to the tree, and you guys can watch the tree until I turn off the stream. Thank you everybody for coming in and watching.